Alright, so in this video we're going to be covering LeetCode problem number 2385, which is amount of time for the binary tree to be infected. So this is similar to the problem in which we have to calculate from a particular target node. We have to calculate all nodes that are present at distance k in a binary tree. So this is similar to that problem, and I have already discussed it, and I'll put the link in the description for that particular problem. You can refer to that before solving this one. So the idea is the same. Let me just go over the problem statement first. That is, you are given the root of a binary tree with unique values and an integer start. So start is the node where we actually start infecting the tree. So at minute 0, an infection starts from the node with value start. Each minute, a node becomes infected if the node is currently uninfected. That is, if the node has been unvisited or uninfected, we visit it and make it uninfected, and the node is supposed to be adjacent to an infected node, right? So if the node is adjacent, then only it can infect it in the next minute. So return the number of minutes needed for the entire tree to get infected. So you see, this is basically a similar problem where we can actually use BFS traversal to infect the trees, right? Since we are going level wise. So for 3, this is our start node, right? So we infect node 1, 10, and 6, right? After infecting this, since 10 and 6 have no, since these are leaf nodes, they have no children, since they have basically null as the left and right children. So we can't go further here, but from here we go over to the left child. So basically at the first minute we have infected 1, 10, and 6. So the first minute we have added 1. Then 5 is infected at minute number 2. Then 4 is infected at minute number 3. Sorry, not adding this, 1, 2, 3. Then 9 and 2 are simultaneously infected because they are the left and right children of 4. So at minute 4, our whole tree gets infected, as you can see. So therefore the output is 4. So that's how you approach this problem, and you see that we are given a binary tree, but in a binary tree you know that we have basically our nodes pointers to our nodes left child, as well as the pointers to our nodes right child, right? But in this case we don't have any pointer that points to the parent, right? Node's parent is not available in a binary tree, so we cannot access going to basically the root or the parent of this particular node, because we only have the left and the right pointers. So in order for us to solve this problem, we first need to convert this binary tree into an undirected graph. So what we'll do is basically use an adjacency list representation, and we're gonna start building our solution from that particular graph, that is undirected graph, right? So as you saw, we have basically seen this example. So it takes 4 minutes for this tree to get infected, right? Similarly, you see this problem. Basically at minute 0 itself, the only node in the tree is infected, so we return 0, right? So 1 is already the node, and it is the root itself, so that is infected. So basically this is how you are going to approach this problem. That is, let's go over to my solution. So it's basically BFS for traversing and infecting nodes, right? So we apply BFS. So the intuition, let us discuss that. So the problem is about simulating how an infection spreads through a binary tree. The infection starts from a given node, that is the start node, and spreads to adjacent nodes, that is the left child, the right child, and also the parent every second. So the main challenge is that in a binary tree, each node knows its children but not its parents, right? So as I was discussing, we need to be able to simulate the infection in all directions, that is up and left and right downwards, right? So left down and right down. So we need to convert the tree into an undirected graph, as I had said, where each node is connected to its parent, left child, and right child. Once the graph is made, the infection becomes a standard BFS problem, and we can solve it easily. So the approach is graph construction. We perform a DFS traversal using a helper function make graph that builds the adjacency list representing the tree as an undirected graph. Then for each node, what we do is we connect that particular node to its left child, its right child, and the parent in case it exists. Parent won't exist in the case of a root. So for basically the root, if this is the root node and we have to start from here, no parent would exist for this, only the left and right children, right? And infection simulation with BFS, we simulate it from the start node. We use a queue, right? So each level in BFS represents 1 second of infection time, and we also use a visited set to avoid revisiting the nodes that we have already visited. And the total time is the number of BFS levels we traversed minus 1. Okay. And talking about the complexity, it's basically time complexity is O of n. Building the graph takes O of n, and BFS also traversal takes O of n. And space complexity for storing adjacency list, BFS queue, and visited set, O of n. Okay. Now this is the main code part. So let us talk about it, how we're going to go through it. So amount of time is our main function, right? And we are given the root, that is the root node, and the start node from where the infection starts, right? And make graph is our function to build an undirected graph from the binary tree. So let us first talk about this function. So basically, make graph would take the unordered map of int, comma vector of int, that is the adjacency list representation, right? So Another graph is an adjacency list representation, and we take the parent and the current node, right? So if the current node is null, we return. That is, we don't have any, since we have a null value, we don't have any node at that point, so we return out of this whole function. If parent is not equal to -1, that is, if the current node actually has a parent, then we need to connect it to the graph, right? So if the parent exists, then we need to connect it to the graph that is already existing, right? So adjacency of current value, we take the current's value and push back the parent, that is, store it in a graph. And similarly, since we are recursively calling this, basically we'll recursively call it after we're done with pushing the left child and the right child. So if current left exists, if the current values left exists, then we push the, basically for our current value, we store the left child, right? So we push back the current left's value. So current ka left ka value we store, and similarly for the right, we store the current ka right ka value in the adjacency list. And finally we call make graph for our currents left, that is for the left child, and for the currents right. So recursively in the left child and the right child, we call the same function in order to build the undirected graph from the binary tree. Now this has been done, right? So once you've made the graph, you basically have converted the binary tree to the graph, and we had passed -1 because the root had no parent, so we have done that. Now we basically we'll store all the nodes that are being passed into a queue. So that is the standard BFS traversal approach. So we've maintained the queue and also an unordered set that would track the infected nodes, right? And we push the start node because we're starting from that particular node. This node is the start node. So here the infection begins at time is equal to 0 minutes. Okay. So we push it and we insert our start into the visited set, that is, we marking it as visited. And min is equal to 0 is an integer which would denote the time. We'll keep updating the time as we go through each level, right? So while the queue is not empty, int n is equal to queue.size, which is the number of infected nodes at the current level. That is, this instead of second, it should be minute. So at this particular minute, what are the number of infected nodes at that current level? And we are basically, while n minus 1 minus would denote that we are going over this while loop, so going over all nodes at current level. Current is equal to queue.front, that is the current, we extract the current infected node and pop it out from the queue, and we check for, basically we are going over all the neighbors of the current node, that is, we are going to infect all the unvisited neighbors. It could be either the child of that particular node, so let us say this is the node, so it could either be the child of that node, that is the left child or the right child, or the parent of the node that we infect in the next level order, in the next level that we traverse, right? So this is the level, let us say this is level 0, this would be level equal to 1, and these are also level equal to 1 since they are connected at distance equal to 1 from the node that we are starting from, that is the current node, right? So from this node we infect all the unvisited neighbors. So we check if wish.find neighbor is equal to wish.end. That means we have not been able to find neighbor in the visited set, right? If we are unable to find neighbor in the visited set, that means neighbor has not yet been marked visited. That means that the neighbor is unvisited, right? So therefore we would push it into the queue and mark it as visited, which means that we are infecting this particular neighbor, right? So once this has been done, this level has been done, we basically increment the minimum counter, which means we are incrementing the time. So one more second or one more minute it should be here, that one more minute has passed, or we have traversed one more level by infecting all the nodes that are present at a distance equal to 1. So once we have covered the distance equal to 1, then all the nodes at a level equal to 2, let us say this is equal to level 2, right? So let us say this was the graph, so, and this was the start point, right? So we have covered the circumference that I have drawn in the circle is basically the level 1 that has been covered. Now this would move to the next level, that is this node, right? This node would be covered, then these 3 nodes would also be covered. So these are standing at level equal to 2 from the start node, and finally we have these 2 nodes which are at level equal to 3, right? I hope you understand. So in this way we keep on increasing the minimum time, right? And finally we return minimum -1 since the last level doesn't cause new infections, right? So we return the minimum -1, and that's how you solve this problem. And let me just basically submit this to show you. And yeah, it has been accepted. So